Now to discuss next remark. But previous lecture we seen that theorem is every coordinate sequence of real number is bounded. Okay, every coordinate sequence of real number is bounded. So converse of this theorem is not true. Okay, remark. Converse of above theorem is not true. Converse of above theorem. Above theorem means every coordinate sequence of real number is bounded. So converse of that theorem is not true. Converse of above theorem is need not be true. Need not be true. So for that example, counter example for this, but before that converse is every bounded sequence need not be convergent, but every convergent sequence is bounded. So this is the converse of above theorem. So for that example is sequence Sn is equal to n runs from 1 to infinity is sequence is minus 1 raised to n. Okay, this sequence is bounded by this sequence is bounded because their range is minus 1 to minus 1 and 1. Okay, their elements is continue only at minus 1 and 1. So this is a bounded by 1 and the bounded above by 1 and bounded below by minus 1. That is, this sequence is bounded above and bounded below. So this sequence is bounded sequence, but this sequence is not convergent. Okay, this sequence is not a convergent. This is a counter example for above converse of above theorem. Then next example is suppose give an example of sequence which is not bounded. Give an example of sequence Sn, okay, where n runs from 1 to infinity, which is not bounded, but for which limit n tends to infinity, Sn divided by n is equal to 0. So here example says that sequence Sn is not bounded, means which has a no upper bound and lower bound, but their limit n tends to infinity, Sn divided by n is equal to 0. So choose a sequence, any sequence. Suppose that sequence Sn is not bounded. Not bounded means which is not either bounded above or bounded below. Okay, so consider for this sequence Sn where n runs from 1 to infinity is equal to root n, where n runs from 1 to infinity. This sequence contains elements. If n is equal to 1, then root 2, root 3, then root 4 is 2. Okay, that is root 4 in this way, which contains an element. This sequence is not bounded by above, but which is bounded below by 1, because bounded this sequence is not bounded above, but which is bounded below by 1, because all elements of this sequence are less equal 1. So this sequence is bounded below by 1. Therefore which is not bounded above and bounded below, therefore sequence Sn is not bounded. Okay, sequence Sn is not bounded, but limit n tends to infinity, Sn divided by n is equal to limit n tends to infinity, Sn is root n divided by n is equal to limit n tends to infinity root n into root n divided by root n, and which is equal to limit n tends to infinity 1 upon root n. When n tends to infinity, value must be 0. Okay, so this is a example of Sn is not bounded, and limit n tends to infinity, n Sn divided by n is equal to 0. Okay, this is an example of our example. So then next is product of two convergent sequence is convergent. Okay, next theorem or example. Okay, whatever may be. If sequence Sn where n runs from 1 to infinity is bounded sequence of real number, okay, and any other sequence, suppose Tn where n runs from 1 to infinity, this sequence Tn converges to 0. Okay, suppose that this sequence has limit is 0 and Sn is a bounded sequence given that, then prove that sequence Sn into Tn, multiplication of these two sequence converges to 0. Okay, so how to solving this sequence is converges to 0? How to solving means product of these two sequence has limit is 0. So how to solving this sequence? Here given that this sequence Sn is bounded and this sequence Sn has limit 0. Okay, so using all of this, here given that sequence Sn is bounded sequence. Okay, sequence Sn is bounded sequence for all n greater or equal n. Okay, and given that sequence Tn is converges to 0, which is converges to 0 means for all epsilon greater than 0 there exist n belongs to I such that Tn minus 0 is less than epsilon. Okay, less than epsilon where n is greater or equal n. So here choose here epsilon as epsilon by m. Okay, choosing epsilon is equal to epsilon divided by m. Then if we choosing, why choosing? Because only for this is greater than 0, epsilon greater than 0, m greater than 0, then their dividation is also greater than 0. So for all epsilon, so epsilon is equal to choosing epsilon divided by m. Why choosing? For arrangement of our theorem here epsilon by m, we choosing epsilon is equal to epsilon by m. Then considering to show here Sn into Tn is converges to 0 as n tends to infinity. Okay, that is to show that Sn into Tn minus 0 is less than any number. Okay, means less than epsilon whenever n greater or equal n. So Sn into Tn, Sn mod of Sn into mod of Tn, sorry here Sn into Tn, which is can be written as mod Sn into mod Tn. Okay, and Sn sequence is bounded by m, and Tn, this Tn sequence Tn minus 0 means mod of Tn is less equal epsilon by m. Okay, this sequence is less than epsilon by m. So putting their value epsilon by m, therefore m get cancelled, remaining only epsilon is strictly less than, therefore mod Sn into Tn is strictly less than epsilon whenever n greater or equal n, and therefore this mod is can be written as Sn into Tn minus 0 is less than epsilon whenever n greater or equal n. Okay, and therefore by definition of by epsilon n definition, this sequence Sn into Tn converges to 0. So this is a very simple proof. Proof of this theorem is let proof. Okay, let sequence Sn where n runs from 1 to infinity is bounded sequence of real number, is bounded sequence of real number. Therefore by definition of bounded sequence, by definition of bounded sequence for any positive real number, m, there exists n belongs to I such that mod Sn is less equal m for all n greater equal n. Okay, this sequence is a, suppose there equation number 1, this sequence is a bounded sequence. So by using bounded sequence, mod Sn is less equal m. Okay, now also given that sequence Tn where n runs from 1 to infinity is converges to 0, that is limit n tends to infinity, Tn is equal to 0. Therefore by epsilon n definition, by using epsilon n definition, for all epsilon greater than 0 there exists n belongs to I such that mod Tn minus 0 is less than epsilon whenever n greater equal n. So here choose epsilon is equal to epsilon divided by m. Choose if we choose epsilon as epsilon divided by m. Why this is epsilon divided by m choosing? Because for rearrangement of to show Sn into Tn, this sequence is connected to 0. Therefore to choosing for epsilon as epsilon by m, this is also greater than 0. Then suppose that this is equation number 2, then equation 2 becomes mod Tn minus 0 is less than epsilon by m. Okay, for all n greater equal n. So this is equation number 3. Okay, now to show limit n tends to infinity Sn into Tn is equal to 0, that is Sn into Tn is converges to 0. This is to show. So consider mod Sn into Tn. Mod Sn is into Tn is equal to, which is can be written as Sn mod Sn into mod Tn, as since by using result mod AB is equal to mod A into mod B. Okay, so using this result, so expressing mod Sn into Tn is equal to mod Sn into mod Tn. Okay, but value of mod Sn is less equal m, and value of mod Tn is strictly less than epsilon by m. So putting their values m into epsilon by m, since from equation 1 and 3, so there which is 1 m get cancelled, and this equal to for this for this step. Okay, so which is less than epsilon. Therefore mod Sn into Tn is strictly less than epsilon whenever n greater equal n. Okay, and therefore this can be written as Sn into Tn minus 0 is less than epsilon for all for whenever n greater equal n. And therefore by definition by epsilon n definition, or by epsilon n definition, limit or by definition limit n tends to infinity, Sn into Tn is equal to 0, that is sequence Sn into Tn sequence Sn into Tn converges to 0. So this is a proof of our theorem. Okay, then next to show that next point is monotone sequence. Okay, monotone sequence. So monotone sequence means which is a bounded above or bounded below, or which is increasing or decreasing sequence. Okay, monotone sequence. So definition, first definition is let sequence Sn where n runs from 1 to infinity be the sequence of real number, be the sequence of real numbers if first element of Sn is less equal second element of Sn is less equal S3 is less equal up to so on, is less equal Sn is less equal Sn plus 1, means terms of Sn are in this form, means first term of Sn is less equal, second term is less equal, third term is less equal, and up to so on. Then given sequence is said to be, then sequence Sn is called non-decreasing sequence or increasing sequence. Okay, Sn is called non-decreasing or is said to be increasing sequence. Okay, non-decreasing or increasing sequence, because all terms are Sn are to get when n tends to infinity, all terms are we get increasing. Okay, so for example sequence Sn where n runs from 1 to infinity is equal to sequence L. Okay, where n runs from 1 to infinity, all terms of this sequence are 1 2 3 4 up to so on, in this way. Okay, so all here 1 is less equal 2 less equal 3. Okay, in this way 1 is less than 2 less than 3, in this way. Okay, so all terms of are we get increasing. Okay, when n tends to infinity, all terms of this sequence are increased. Okay, therefore this sequence Sn is a increasing sequence. Okay, it's increasing sequence or non-decreasing sequence. Okay, so next definition is decreasing sequence, decreasing or non-increasing. Next definition is reverse of this sequence. Let sequence Sn where n runs from infinity be the sequence of real numbers if S1 is greater or equal, S2 is greater or equal, S3 is greater or equal, up to so on. Sn is greater or equal, Sn plus 1 is greater or equal, and up to so on. Then given sequence is called non-increasing. Then sequence Sn where n runs from 1 to infinity is called non-increasing or decreasing sequence. Non-increasing means decreasing sequence. Okay, means this sequence is not increasing, this means that which is decreasing sequence or decreasing sequence Okay, this is a definition of increasing sequence, this is definition of decreasing sequence. Then next definition is monotone sequence. Monotone sequence which is in every sequence is every increasing or decreasing sequence is monotone sequence, means which is either increasing sequence or decreasing sequence, then we say that given sequence is monotone sequence. Okay, if sequence Sn where n runs from 1 to infinity is either is either is either decreasing, or here decreasing, other name is non-increasing, is either decreasing or increasing. Decreasing or increasing has no other name is non-decreasing. Non-decreasing. Okay. If sequence Sn is either increasing or decreasing, then we say that sequence Sn is a monotone sequence. Then we say that sequence Sn is called monotone sequence. Okay, monotone sequence means which is either increasing or decreasing sequence. Increasing sequence means all terms are increased. Okay, and decreasing means all terms are when n is increased, then their terms are decreased, and here n is increased, then their terms are also increasing. Okay, so in this way, this is a definition of increasing sequence, decreasing sequence, and monotone sequence. Okay, so example, suppose that, for example, Sn is equal to 1 by n, where n belongs to set of real number. Okay, or sequence Sn, n runs from 1 to infinity. Then this sequence their terms are 1, 1 by 2, 1 by 3, 1 by 4, 1 by 5, and up to so on, lastly 0. Okay, lastly 0 when n tends to infinity. When n tends to infinity, then their term is lastly 0. Okay, so yeah, this sequence is increasing or decreasing. Here clearly we see that clearly we see that n is greater than 1 is greater than 1 by 2, 1 by 2 is greater than 1 by 3, and up to so on. Okay, means all terms of this sequence are decreasing. Okay, when n tends to infinity, means n is a increase, then these terms are value of these terms are decrease. Okay, so this sequence is a decreasing sequence. Okay, that is non-increasing sequence. This sequence is decreasing sequence, that is non-increasing sequence. Non-increasing sequence. Okay, this is one example. Second example, suppose that n runs from 1 to infinity is equal to minus 1 raised to n. Minus 1 raised to n. This sequence is neither increasing and nor decreasing. Okay, this sequence is nor increase nor decrease, so which is a constant sequence. So their elements are minus 1, 1, minus 1, 1, and up to so on. Okay, this is neither increasing or neither increasing nor decreasing. Neither increasing means non decreasing, decreasing means non increasing. Okay, therefore this sequence is neither increasing and nor decreasing. Therefore this sequence is not a monotone sequence. Okay, because monotone sequence, definition of monotone sequence is either increasing or decreasing. So this sequence is neither increasing nor decreasing. Therefore it is not a monotone sequence. It is not a monotone sequence. Okay, so this is a monotone sequence. Okay, this is increasing sequence, this is monotone sequence. When sequence is either increasing or decreasing, then we say that given sequence is monotone sequence. But then reverse of our statement is, if sequence is neither increasing nor decreasing, then we say that given sequence is not monotone. Okay, so next lecture is theorem.